lectures at the International Congress of Mathematics in both 2018 and also this year in 2022. He is fascinated by finding the extraordinary in the ordinary, especially in mathematical, especially in physics. And this morning I learned that he was born on the exact day that Lev Landau, the famous physicist, passed away. And so maybe there's a connection there. Please help me welcome our speaker today.
Thank you very much. I'll check. This microphone is working okay. Billions of people around the world, every morning as the sun rises in different parts of the world, from a cup like this. And one day, when I finished my morning tea, it occurred to me to tap the cup. Anywhere I tapped, tan, 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 I got the same pitch. And I got the same pitch. So this is perhaps the characteristic pitch of the cup, and if you take another cup, it will be another pitch, and so on, high and low notes. But then it occurred to me to tap in slightly different positions, 45 degrees off. Oops, how do I go back? We were doing here. How do I escape? If I tap at those 4 points, tan, 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 rather than tan, 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 you get a higher pitch than before. What is going on? So it's something mysterious is going on. Well, thank you very much for pointing that out. It has to do with, obviously, the handle. But if the handle is the culprit, wouldn't you have guessed, as I guessed first, that somewhere and the handle should behave differently. Not how the symmetry is broken. Indeed, this half of the cup and that half of the cup seem to behave the same way, but closer to the positive. But at 45 degrees off, you get a different pitch. So why is this happening? I'd like to give you a zeroth order approximation, which leads us to all sorts of interesting mathematics. That's the world of Fourier analysis. So giving you the same pitch about timing. So please ignore this handle. And you see at this point, remember the handle is not there. You make this point vibrate like this, in and out. Well, in response, the point that is diametrically opposite can do one of the two things. It can respond like this, or it can respond like this, in or out of phase. Is that okay? But now, this first of the responses like this is essentially sort of a rigid body motion. The entire cup is moving back and forth as a whole, and it's not deforming the shape of the cup, and the sound has everything to do with the deformation of the shape. Yeah? So this mode you do not hear. What is being heard is this mode. But a cup wants to stay incompressible, not to be confused with incomprehensible. So as far as possible, it wants to stay the same volume, and when those 2 points go in response, those 2 points go out. And when these come in, those, and so forth, so forth. So you see any square worth of points work in unison and start singing like this. Okay. So the same thing if I tap any of those points and so on. Now, why those 4 points emit a higher pitch than those 4 points? In order to understand that, let's bring back the handle. Resurrecting the handle, we see that when you tap any of those 4 points, we saw that they sing in unison. But you see, when they move, they have to move the point where the handle is attached. And a very hefty mass that they have to move with them. Yeah. Whereas when you tap one of those 4 points, you see what happened when this point goes in, this point comes out, and these do like that. So in between, the point is, to a good approximation, not moving. In other words, those 4 points, square points, working in unison do not have to move the handle. As far as they are concerned, the handle is not there. So now, ladies and gentlemen, you have two elastic systems. If you like, you can think of them as springs. One of them is attached to a very hefty mass, and the other one is not attached to anything. And when you release them, what happens? Well, the heavy one will go whoa, 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 and the lighter one will go hee-haw, hee-haw, and that's the difference. Okay, so this is very, very satisfying, and it's not coming back. Okay, and okay. So far, we knew where the handle was and figured out what kind of sound pattern we get out of this. In other words, we knew all the conditions and we had to solve the problem, so to speak, forward. If you speak in the language of partial differential equations and so on, you know all the boundary and initial conditions and you wanted to know what the solution was. But since we're talking about pitch, let's imagine that we go backward. In other words, imagine yourself to be in a pitch dark room. And you don't know what the cup looks like or what it is. But you're allowed to walk around the cup in all sorts of positions and record that sound pattern. Question. From that data of the recorded sound pattern, can you reconstruct what the cup looks like? This is what is called inverse problem. In other words, you don't know the conditions, but you know the observed data that came out at the end. And given this observed data, what must have caused it? You work backward in the chain of causation. And if you think about it, much of life is about solving inverse problems. It is epistemologically extremely important to be used to inverse problems. And of course, there are some experts in this. So how can you reconstruct a cup? And you saw already this simple example. This simplest of the inverse problems cannot be solved. You probably have the intuition that whether the handle is at the east, north, or west, or south, you would get basically the same sound pattern. Yeah, you cannot tell where it is. And also, even worse, motivation, have a very large handle in one position, or maybe two medium handles in opposite positions, or four handles, and they'll produce the same pattern. In other words, symmetrically, you can do all sorts of things. But up to symmetry, in the mathematical jargon, if you mod out by the symmetry and go to the quotient, you can start making progress. And this is a very, very standard situation in inverse problems and so on. So you see that kind of problem. Okay. That was a vibrational system in some kind of 1 degree of freedom. But now I would like to regale you with something else which has more and more degrees of freedom. First, not so many degrees of freedom. The cup that comes back from here. Give me in good stead. So here is something that I actually genuinely bought with my own money, and I don't know if you can see this. It says on the cover, Chai Gruzinski Extra, found on the street market in Bordeaux many years ago. It says extra quality Georgian tea. And when you open this, it's too small to see. It gives you a very scientific instruction on how to brew a good cup of tea. That has nothing to do with my experiment. I'm just carrying around cedar balls. You know, the kind of balls that you put in a closet in order to chase away moths and so on. Okay. The one thing to be said for this experiment is that it smells nice. You can't say that about many experiments. And so you put 2 or 3 balls in here. And then can you see it's a bit in the shade, but okay. So I put 2 balls and then swirl this cup. By swirling, I mean, English is very rich in verbs of motion. Most of them seem to start with the S. When I swirl, I mean this, okay? I don't mean this, which would be spinning. So I keep inside this translation subgroup, as it were, but I impart to all the points at the same time circular motion. That's what I mean by swirling. And when I swirl, you see that those cedar balls circulate in the expression that you expect, which is in the direction that you expect, which is in the direction of swirling. Okay. But now I increase the number of balls. And I don't know if you can see, this is a bit too deep, isn't it? No, it's the light is not. It's a bit of a problem. I think you can kind of, when I swirl, can you see they start circulating in the opposite direction? You see, maybe it's hard, barely visible. So what's a good to do? I'm going to, excuse me, of the deal, I'm going to do something very strange here. Yeah? Is that visible? A little better. When I swirl, they start circulating in the opposite direction. So I'll take one more. I don't know, this is very convincing. Okay, you come to the front after the lecture is over, and then you'll see. Okay, I apologize for recording kind of thing. Okay, so when you have one or two balls, they are circulating in the correct direction, but more and more balls, they start circulating in the opposite direction. In other words, there's some kind of phase transition. Yeah? The response suddenly changes qualitatively. And you saw that 2 balls, they are circulating in correct direction, 3 balls, and so on, 4 balls and 5 balls, they are still. And 6 balls, in fact, they start hesitating, and 7 balls, they definitely start circulating in the opposite direction. Okay. So maybe I'll try one more time my luck. Okay. Can you see that they're circulating in the opposite direction? Yeah, you can kind of, yes, you can see that, okay? Yeah, that's better, right. Okay, so there is a phase transition. And it is really a kind of phase transition in the following sense, that you see, what's happening is that when you have few balls, those balls are not talking to one another. They are so sparse that they are, very far away from one another. They are independent particles which are being driven by the impact wall. And if you are impacting like this, they circulate in that direction. No problem. But when you have lots, so in other words, it is a linear momentum dominated motion. You get momentum in, and the momentum is what's driving them around. However, when you have a lot of them, order parameter is the density or the crowdedness, then whatever momentum comes in from the side gets lost, among the contacts, among the neighbors. They are scattered and they are wasted. But what is not wasted is the rubbing against each other. So if you have, like a cogwheel, if you have one ball which is moving like this, the other ball starts moving in the opposite direction and so on. So those rotations are transmitted from ball to ball towards the middle, and they started sort of dancing in the opposite order. In other words, it is an angular momentum dominated motion. And as I said, the difference is how crowded they are. So initially, it was really like a gas because all the balls are independent. And then later on, it becomes like a liquid because the points are in contact with one another. So the contacts do matter, but they can still slide past each other. And to show you that it is really a phase transition, if you increase the amount of balls and the number of balls really a lot, then they kind of freeze solid. They don't move anymore. Okay. And so that's the kind of thing. All right. Okay. Next, I'm going to give you another curious experiment. This time, it will be much easier to see. So please. This is a gift from Andy Ruiner, who thought about this kind of thing very, very deeply. And I used to go around the US many years ago, 2 decades ago, saying that this kind of thing must be possible. But one year I was really shocked that Andy had worked it all out. And in fact, he sent me as a Christmas present one year. So those 2 heptagons, 7 gons, regular 7 gons, I would like to assure you of 3 things. They are, number 1, made of the same material, same alloy. Number 2, they have the same surface coating. There's no problem about that. Number 3, and they have the same mass and so on. Number 3, and what is most important, is that they have the same mass and mass distribution is uniform as you see. In other words, there's nothing hidden inside. You see, for example, there are spokes, and it's not the case that, inside the spoke is hollow and so on and so on. Where you think the mass is, that's where the mass is. There's nothing hidden inside. It's just a solid object, which is really stupidly uniform. Okay? So I assured you of 3 things, that they have the same mass and so on. However, when you try to roll them, this one rolls rather well. I can manage to roll it. Okay? But this one refuses to roll. And it's actually better to do it other. So if I try to roll them, one of them rolls much better than the other. So this one rolls better. Okay? So, it's not working. The reason is, okay, I'm going to turn it around and I'll do it on this table. On the wood table, it's much, much better. Sorry. So, Here, can you see? And a bit in the shade. So this one rolls no problem. Okay? No problem. But this one refuses to roll. It just simply will not roll. So if I try to roll them at the same time, one of them rolls, but the other one does not roll. Okay. So this is the rolling one. And this one simply does not roll. It stops, and if you try to force it, it falls flat. Okay. So there's a definite dynamical difference between those two things. And the question is different? They look the same. Now, you are probably coming up with theories about difference, but please remember, whatever there is difference, that difference is very, very small, because after all, you cannot really see the difference. And you have to convince yourself that such a tiny, invisible difference, mind you, can cause this really visible dynamical difference in behavior. In other words, this behavior is absolutely structurally unstable. So what is causing the difference? It turns out that the difference is quite ingenious. And it's given in the following. The one that rolls, well, one that does not roll, let's start with that. The one that refuses to roll is just a regular heptagon. All the sides are straight. But the one that rolls is a regular heptagon whose sides have been curved out slightly to make it strictly convex. Yeah, so it's a bit like this. And when you try to roll such a thing, watch what happens. You start from vertex, and you transit to the next vertex, and the point of contact can transit continuously from one vertex to the next. Okay. So that's very nice. But as that is, however small this rounding is, that transition is continuous. But when you make it flat, as soon as rounding, call it epsilon, becomes 0, and you try to roll the heptagon, look, while this is coming down, the point of contact or the pivot is always at the same vertex. You cannot move. And so it's just falling around that pivot until bang, the entire edge comes in contact with the floor and dissipates energy and motion dies. And this is quite remarkable because that's very different from epsilon, tiny, but not 0. So we are in the presence of what is called singular perturbation, one of the major things about life. Some that depends on parameter epsilon. And for every epsilon non-zero, the system behaves in a certain qualitatively the same way, it's boring and so on. But when epsilon is 0, the behavior suddenly changes. In other words, the of the model behavior as epsilon goes to 0 is not the behavior of the model at 0. You cannot take the limits. There's a discontinuity there. Okay. And the reason, by the way, the first experiment on this table did not work is that this table is very soft. So when the table is soft, that softness of the table hugs the shape of the heptagons and so on, whereas the wood is harder, so that works much better. Yeah, you can imagine that, for example, on the carpet, this experiment, and this took me by surprise, but this is a good opportunity to play. So if you do this experiment on the, for example, extremely hard surface, it works really strikingly, yeah, and so on. So, okay, so that's the what was going on. This was several degrees of freedom, so many degrees of freedom. Now I shall put up the ante and will give you more and more degrees of freedom. In fact, infinitely many degrees of freedom. Every once in a while, you happen to meet a person who is carrying around an inclined plane, and here I brought 2 jars. One of them is full of very nice rice from India, basmati rice from India, and the other one is full of very nice air from Seattle. And so this is full and empty. Let's call them 1 and 0. Okay? And I propose to let them roll down this slope. And it rolls down very nicely. It rolls down very nicely. Yeah. And I should say this is the full one. What happened to this? I'm losing my eyesight, that's why. So this is the full one, excuse me, and it rolls down nicely. And that rolls down nicely. And the full one and the empty ones roll down more or less. Sorry. I shouldn't apologize. Okay. I'm losing my eyesight, that's why it's not happening. Okay, this one rolls down, and this one rolls down. Okay, so they roll down quite nicely, and roll down more or less at the same rate. Okay, now what I would like to investigate is what happens if I change the amount of filling inside. So instead of the full one, let's take it maybe half. Will it roll down at the same rate or what? And in order to make the contrast rather clear, I brought here two prepared jars. One of them is 2/3 full or 1/3 empty, depending on your optimism. And the other one is 1/3 full. So 2/3 and 1/3. So what will happen when I try to roll them down the slope? Okay. So remember the full one, 1, T1, 0, roll down pretty fast at the same rate. What about the 2/3 one? Okay, there are three possibilities on there. Number one, maybe it will roll down slower than the 0 one. So if you imagine plotting, as I shall do in a moment, the rate of descent as a function of how much rice there is inside. At 0 and 1, we had pretty high data points. Yeah, they roll down pretty fast. How about 2/3? Will it go down faster, slower? Those are two possibilities. Maybe it will be slower than those two, or maybe faster than those two. Or if you believe in the story of Galileo dropping, things from the Tower of Pisa and so on, maybe the rate of descent has nothing to do with the amount of mass inside. So maybe it will be at the same speed as or same rate, acceleration as the other two. So let's take a vote. Who thinks the 2/3 one will roll down faster than 0 or 1? Who thinks the 2/3 one will be slower than 0, 1? Oh, congratulations. This is what the most reasonable citizens vote for. So yeah, I like that. And who thinks it will go down at more or less the same rate as 0, 1? Yeah? Okay. So that's the majority vote. Let's experiment. 0 and 1 went that down. Now 2/3. It goes down rather slower, more gently than 0, 1. And again, afterwards, maybe you cannot hear it so well. There's a lot of sound going on inside. This table is not flat. Okay. That is because there is some kind of avalanche that is going on inside. So all the grains actually are stuck on the inside wall. And then when they emerge on the free surface, they avalanche down that slope, and then they are making that noise and in fact dissipating energy by collision and all that kind of thing. So what we have here is, okay? It will come back, okay. Okay, so what you have here is, I'm sorry. Sorry, I'm kind of, I'm terribly sorry about this. Okay, what you have here is something very dissipative, and it's noticeably slower than 1 or 0. Okay, but it remains for us to test the other possibility, which is 1/3 full. Okay, so now there are 4 possibilities on there. So maybe the 1/3 full will be faster than everyone that we have tried before. Or maybe it will be slower than everyone. Or maybe it will be, you see, the 2/3 was pretty slow compared with 0 and 1. So maybe it will be faster than 2/3, but slower than 0, 1. Maybe in between. Or if you believe in symmetry, and if you have a beautifully symmetric mind, maybe there's a symmetry between f and 1 minus f, if you see what I mean. So maybe 1/3 and 2/3 will go down more or less at the same rate, as will maybe 1/4 and 3/4 or something like that. After all, there is already one data point. 1 and 0 go down at the same rate. So who thinks, let's take a vote. Who thinks it will go down faster than everyone? 1/3. Okay. Who thinks it will go down slower than everyone? Okay. Who thinks it will go down at the same rate as, who thinks it will go down faster than 2/3, but slower than 0, 1? So that's not the absolute majority, but that's the large number. And this is the version that the option that most honest citizenry will vote for. So who thinks it will go down as fast as at the same rate as the 2/3? So those are symmetrically minded people. Okay, let's experiment. Okay, so nothing up here, nothing up here. So I'm going to do the 1/3. Okay, are you ready? So I'm going to release. It stops completely dead. 0. Not only is it 0, but even if I try to coax it to go down, it refuses and stops. Completely immobilized. That is quite interesting. And that's what I shall say. So why did if you fill the jar almost to the full, that was 2/3, did it go down slowly? But then if you decrease the amount, it got immobilized. Why is this? Well, static theory is actually very, very charming. In order to do this, I will tell you of the basics of granular dynamics. And the key concept is what is called angle of repose. I am sure you remember going to, as a child, or maybe with your children, to make a sand pile. Yeah, I'm talking about dry sand, by the way, because with a wet sand you can do all sorts of strange sculptures, but with dry sand, and you notice that there is only so much angle that you can get in steepness of dry sand. If you try to make a dry sand pile too steep, it avalanches and settles in some angle. Okay, in case they are experts in granular dynamics, indeed, angle at which the avalanche starts and angle at which the avalanche stops are slightly different, but that's not going to be relevant for our discussion. So let's angle of repose. Okay. Of sand. Okay. And for any grains, there is that. Now, the thing is, this angle that I did by alpha, interesting thing. For example, liquids cannot sustain any steepness. So if you have, let's say, syrup or honey, indeed you can make a bump on the surface. But if you wait long enough, it will settle down to completely flat, right? So alpha is 0 for them. Okay. Now, an interesting claim, and in fact, a theorem, if you like, or law of nature, this angle alpha, angle of repose, does not depend on basmati rice is long and thin, so that it will give you an angle of repose different from if you had spheres and so on. But it does not depend on the size of grain. And I shall prove for you. Are you ready? Proof. Make a sand pile and look at it from very far away. Grains look small, don't they? And you come close and they look very, very large. But it's the same angle, QED. Okay. So it does not depend on the size of the grain. This shows that you might naively think, well, it's nice to have a theory of granular flow, and in the limit of the grains becoming smaller and smaller, it's going to become a fluid, and it will become hydrodynamics. But that's not true, because angle of steepness, angle of repose will be something, all constant, and at the end, when the grain becomes 0 size, becomes boom, suddenly 0. So there's a discontinuity there too. There's a singularity in the theory. In other words, you cannot take the limit of the theory and then try to recover hydrodynamics at the end. There are all sorts of situations that we're meeting throughout this lecture where this is singularities in the theory. Okay, so with that in mind, here's what happened. Let's say that you have also a lot of grains of sand in the jar, and what you have is depicted in the picture there. So the point of contact with the slope is depicted by red. The center of gravity of the grains inside is kind of there. You see, it's a green. And the gravity is, of course, pulling you downward, as the state of Washington. And so it's going down. And you see that this gravity is passing on the downhill side of the point of contact. Lots of grain. So the effect of that gravity is to exert a torque, sort of rotational tendency, which will roll you downhill. In contrast, suppose that you have very, very few grains inside, a little grain. Then you can arrange matters so that the center of gravity of that mass of grain is on the uphill side of the point of contact. So that the gravity is still pulling you down, but the effect of that downward pulling gravity is actually to roll the jar uphill, thereby resisting the downhill motion. And in between, of course, there's a amount of grains which will make the gravity go, pass through the point of contact, and then what it is doing is to sort of go rock back and forth in order to find that equilibrium. And I'm going to show you in the experiment. So if you have that, and initially when I release it, I don't know if the resolution is good enough. Watch. So it rolls back and forth a little bit. Yeah. And then finds the equilibrium. Okay, so this is what's happening in the quasi-static theory. you also, this is a mathematician's care, but you realize that this happens only in particular, if you have something that is liquid, so angle will is horizontal surface, and the center of gravity is always going to be on the downhill side. So you cannot have a liquid having this effect. You have to have grains where the angle of repose is non-zero. But it's interesting to do this experiment with liquid as well. I did it at home. So and then put it on this very inclined plane. And then I thought that it would go down very slowly, as the liquid, in this case honey, flows very slowly. But that's not what happened. In fact, what happened is that it didn't move at all after a little bit rocking. And I was very offended by this, and so I watched, and the watched jar does not go down the slope apparently. So it's just, and I got really bored and went out and got myself a cup of tea. Came back 5 minutes later, and he had moved a certain distance. What? And then I watch and nothing has happened. I go out of the come back and he moved a little. I thought it was my son who was doing this, but no. And it turns out that there's some intermittency that appears spontaneously. So it just doesn't, and as something is flowing, it goes stonk and then stops. And then something flows and stonk, stops, and so on. So it's an intermittent discreteness appears from this continuous system. It's very interesting. And you can also use it as a clock. And how much time does it go down? So it's really a curious system. Okay. So if I drew the graph of this rate of descent, the descent pace, as a function of how full the jar is, I saw that the 0 and 100%, they are more or less going at the same rate. But in the middle, there's a whole base of the immobility, amazingly. And moreover, there's something that is quite interesting. On this side of the base of immobility, that is, on that side, on the right-hand side, so there are more than, say, 2,000 so on, you saw that it went down slowly. And also, when it went down slowly, what happened is that you had this kind of colloidal shape of the free surface where there were avalanches of this is behaving like, if you know anything about viscous fluids, like a viscous fluid. In other words, no slip boundary condition, and on the surface there's some kind of avalanche, and then it's dissipating energy because of the contacts and so on. It's behaving like viscous energy, a viscous fluid. Okay. What happens when you do the, when you step 2? That is interesting. So 1/3 was in this basin of immobility, but let's decrease the grains even further and see what happens. Here it is. So very few grains left. And now I'm going to release this. And maybe the resolution of the camera is not so good, but I'm going to help you see it. When I release it, it will go down. But it goes down in a rather interesting motion. It kind of is a bit rickety. And also, again, you have to come in front after this to watch in detail. But the grains are not avalanching at all, but they kind of stay as one single body, and they're sliding inside the jar. Okay. So there is no avalanching, there is no sort of moving together with the inner wall of the grains. So what you see is this. All the grains are kind of staying together, and then they're sliding back and forth inside the jar as the whole shell is going down. So you have a slippery boundary condition, and there's practically no dissipation except for this friction and so forth. So it's behaving a bit like inviscid fluid. Slippery boundary condition. Yeah? And now, those of you who have studied and liked fluid mechanics will know that the theory of viscous fluid and that of inviscid fluid are really at odds with each other. First, the boundary conditions are different, and then you cannot take the one into the other by taking limits and so forth. So these are very different physical phenomena and extremely and incompatible, may I say, mathematical models. But this is one of the first and certainly the simplest physical experiment where those two mathematically incompatible regimes are present at the same time in different parts of the experiment. So with Nicolas Taberlet, who was very clever, who is a very clever physicist at the École Normale Supérieure in Lyon, and I been playing, what we would like to do is somehow arrange the system so that basic mobility becomes narrower and narrower and narrower, and force those two regimes, that is the viscous fluid regime, to meet. They are mathematically incompatible. So Mother Nature will have really a hard choice to make there. In other words, I really want to break the mathematics and see what happens. Yeah? And that's what I'd like to do. Was a large, many degrees of freedom, and I would like now to show you another experiment, which you should see directly. So here is, in fact, having said directly, I will also switch on the camera. Here is a toy which I brought from Japan. It's very traditional in my country, and it's just a paper balloon with a hole here. Yeah? Because there's a hole, I can inflate a paper balloon by blowing into it. And then it inflates. Okay, it becomes round. But there's another way of making it round. I can crumple it, and then I can tossing it in the air. Now, by striking it all directions, it's very random striking. You would think you are going to dent a ball that you are striking in all directions. Yeah, you are going to dent it. But look at what's happening. It's becoming rounder and rounder as I try to dent it. I'm just, oops, sorry. I'm just tapping it in all sorts of directions. And it has. This is a way of making something round by trying to poke it. And although I'm not going to do it, something even more shocking is true. So, okay, let's eliminate gravity. And it will take a longer time, but I can actually crumple this and start striking it with my finger on the table in all directions. With a finger, so I'm really poking it and trying to dent it. But it turns out after 20, 30 minutes of really patient poking and so on, it becomes round and round and it becomes completely round. So what is this? By poking, I make something round. It is really strange. So what is happening is the question, and it leads to another kind of singularity. Control, I can't deal with this. Okay. So here is in some sense, a toy model, again, of this toy system. Let's crumple this and see what happens. And in fact, the key is, before I show you this, this is made of paper. So when I crumple it very hard and watch what happens, it starts kind of coming back a little bit. It doesn't stay crumpled. It has a little memory and it wants to relax a little bit. And that is key. Okay. Imagine one of the steps of this ball crumpled them on both sides, left and right in the picture. And I hit very hard from the left. What happens at the next moment of time? Because of that, boom, side gets. On the other hand, hit super, if you like, wrinkled, because I hit it really hard. Okay, so on one side, I rounded it. I don't know, I broke even. But now this memory comes in. The super wrinkled side starts coming back, relaxes from the wrinkles, and basically recovers same wrinkliness that I had before. So after this cycle, the net effect is that I increase the total wrinkled but came back. Okay, so per cycle, I increase the volume. And that is, of course, what I wanted. I want to keep increasing the volume until it becomes the maximum volume, which is the sphere. So plot the volume as a function of time. Each time I hit, volume instantaneously goes down, but then it recovers. Yeah, and hit, recover, and it asymptotes to this sphere. And that is what's going on. This is actually a very, very remarkable system if you look at through the lens of turbulence. You see, in many, many physical situations where lots and lots of different scales are cohabiting, so you have small scale, middle scale, large scale, and so forth, there is often what is called a cascading phenomenon. For example, in the theory of turbulence, it's very, very traditional since the time of G.I. Taylor, then Kolmogorov, to regard the system as lots and lots of vortices that are mixed together. Yeah, vortices that are small, vortices are very, medium, vortices are kind of a little larger, vortices are huge, gigantic, and so forth, and they are all sort of interacting one. But now, what happens almost in all multi-scale systems, from large-scale system, there is some sort of trickling down. For example, in the case of turbulence, you have large vortex, which gives down some of the energy to medium-sized vortices, and in turn, each medium-sized vortex releases some energy to small-scale vortices, and even tinier vortices are the next recipient, so on. But if the vortices become too small, they lose the energy to viscosity, and then they go out. Okay, so there's a cascading from top to bottom. Because the energy is being dissipated at a small scale, you have to keep pumping in the energy from the top, and that is called stirring. So this is the picture of the turbulence. In all the naturally occurring multi-scale systems, physically there is a cascading of energy, entropy, information, what have you, from the top to down, large to small. Yeah. In this picture, you see when you start, you had lots and lots of small wrinkles, and then they gave rise to slightly larger wrinkles, the wrinkles larger and larger. Eventually, when the wrinkle size becomes as large as the size of the sphere, it just stops being a wrinkle, and then it just disappears. So you have what is cascading from small size to large size. Now, those of you who are experts in fluid dynamics will probably object, but in two-dimensional turbulence, there is inverse cascading. Yes, but that's a fascinating mathematical problem, but in two-dimensional system, there's no vortex stretching and so forth, all the mechanisms are out of the window, so it's a fairly artificial thing. So in natural systems, really natural systems, I don't know of any other system where the inverse cascading occurs, but this is one example. Yeah? So it's something really strange going on, that this kind of cascading is the agent, if you like, of shape formation, if you like, morphogenesis, and the shape that you achieve is optimal, that's like the sphere. Okay. Thanks to the inverse cascading, which is really strange. Now, let's go back and really face the greatest and most famous singularity of all. Here is a support that I brought, and a big, big coin. Does anybody have a coin that I can borrow? A coin. Do you have a coin? Any money? Thank you very much. Madam, do you have a coin? So nobody has coins in this country anymore. Thank you very much. That's very, very, yes, you are very reliable. So here's a coin. I think Jack lent me. And when the coin drops, a penny drops, you hear this very characteristic noise. It jitters or shudders to a halt. It's characteristic that when you hear this in a pub or in a cafe and so on, you know, somebody dropped the coin. Yeah? Okay, so you hear this. Okay, thank you very much. So this one, this is a really, really large exaggerated coin. It's so large that you can't believe the kind of trouble I get into at airport securities and so on. But it's very, very large, and I'm going to ask Jack. So can you weigh and tell people that it's very heavy?
It's very heavy.
Thank you very much. Thank you. So for your services, I'll pay you a quarter. And so it's so heavy that when I launch this, the experiment lasts for long. The dynamics lasts for a long time, and because it lasts for a long time, you can see some interesting features escape our attention otherwise. It's going completely spontaneously. I'm not driving it with any motor or a magnet. It's just going on its own. It's purely inertial. And as you might see from the kind of reflection on the top, it's actually not spinning faster. It's spinning at this constant rate. But nonetheless, you hear something's going faster and faster. What is accelerating? Something's going faster and faster, but it's not a spin. It's going faster and faster. The motion is lasting longer than I thought, but it's going faster and faster. And eventually it will come to a stop, but when it does, please pay attention to how it stops, especially listen to the noise that it emits. Faster and faster. Faster and faster. faster and faster. It will stop in 40 seconds or so, I think. And do you hear that? Something went through the roof. So the pitch was rising, and it kind of diverged. So what is happening? It's very, I'll repeat the experiment, but only then. Yeah, amazing. Well, this phenomenon captured the imagination of many people about now 20 years ago, maybe 15, almost 20 years ago. And lots and lots of people got interested in this. And in particular, there was a paper which became famous that appeared in Nature, no less, which claimed that this effect, this noise that somehow diverges, has to do with the friction of the air that's trapped underneath the disk. So it's lubrication theory. And many people didn't like this. And so there were some people writing, for example, from California, I believe, who said that, well, they did the vacuum chamber experiment, and then they saw, of course, not noise because it's vacuum, but they saw the same sort of shuddering and sort of, frequency rise and so on. And it's the same thing in the vacuum. But that's actually not conclusive, as the author of the Nature paper said at the time. It was known to Maxwell that, okay, if you make the chamber more and more vacuum and decrease the density of the air, you might think that viscosity of the air is going to decrease, but that's not the case. It turns out that the viscosity of the air is almost independent of the density of the air or of any fluid. And that's because of course, what is viscosity? Well, you have lots and lots of intercollisions of particles and so on, and they start exchanging momentum and so on. So that's what it is. And if you have low density, of course, collisions don't happen so often. On the other hand, so what is called mean free path between collisions, how long this travels, increases if you have less dense medium. And so that carries the influence much longer. And if you look at from the kinetic theory of gases, the formula for the viscosity, the density and the mean free path come as canceling factors. So they cancel each other. And so if you decrease the density, the viscosity is basically constant. So in experiments, you keep decreasing density and the graph of the viscosity constant. Only at the end, when the density becomes absolutely zero, it suddenly drops and becomes zero. So it's extremely difficult to do a vacuum chamber experiment that gets rid of the viscosity of the air, effect of the viscosity of the air. So that kind of thing is probably. At that time, I was a postdoc in Montreal, a very much struggling one. I was on a 1-year contract from year to year. And then I had some idea of my own, and I had worked out a model, but I wanted to do an experiment. But vacuum chamber is very expensive. I couldn't afford it. So I went to an accessory shop and bought this. Yeah, it's a cheap bracelet. Yeah. It was rather embarrassing because I went to an accessory shop and then started spinning one thing after another, and then to see which one worked better. And the very charming assistant came and said, "May I?" And so there is no question of the air trapped underneath this, simply because there is no disk. Yeah, it's empty. But now I'm going to launch it, and let you watch what will happen. I try to launch it nicely. So it's like a ballerina who's spinning vertically, and it's vertical, but that's the first motion. Soon she'll become tired and transit to second regime motion, and you'll see what happens. Fairly stably first regime, it's vertical, spinning, upright spinning. But now she's becoming tired, and soon we'll have a transition. Very sudden. Now. And from that point onwards, it's the second regime. For all intents and purposes, it's the same motion as the disk. And it's the same thing. Okay. And there is no air trapped underneath the disk. So, what is happening? I'd like to understand this motion as a very linear superposition of two motions, if you like. One is spin, the other one is flapping motion. And if you think about it, if you are flapping while spinning, you get this kind of sort of motion, which is exactly the rolling of the thing. Okay? So what is speeding up is not speeding up, it's no angular momentum from outside, rather the flapping, which is getting faster and faster. Or if you like, very simply put, if you look at the point of contact with the surface, it's going round and round, faster and faster. And in fact, theoretically, it can go round and round infinitely fast and exceed the speed of light and so on. And you're going to say, oh, no, that's wrong. But actually, it's not wrong, because what relativity prohibits is a transmission of anything, material or informational, faster than the speed of light in a vacuum. Some geometric condition can travel faster and faster and beyond the speed of light. For example, suppose that you have what is called a wave in a stadium and so on. So you line lots and lots of people along a straight line, and you tell each person at such and such time, such and such clock, and such second, you stand up and you sit down. Okay? You just arrange matters so that they all sort of do the same, do as you are instructed, and you can make that wave travel faster than the speed of light. No problem, right? Of course not. Because they are not talking to each other, there's no information that is being transmitted. So, no, there's nothing wrong with going faster than the speed of light. Did you know that? You should remember this. So here, geometric condition can go around infinity fast, there is no problem. Yeah? No information is being carried and so on. There's a standard, which I don't have time to tell, but later on during the question session, I will tell. Here, analogy that I would call you to your attention is the one of bouncing ball. If you have a ball bouncing, dun, 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 the frequency increases and theoretically diverges. Okay. It is a very, very nice example of a geometric series, which solves this problem, which says that, well, it bounces theoretically infinitely many times, but this motion stops after finite time if the coefficient of restitution is less than 1. And also the frequency increases and then eventually diverges at the end. So what I would like to propose the analogy between bounce for this bouncing ball and flap for this disk problem or the rim problem, circle problem. Okay, and if you accept that analogy, the following becomes possible. So let's estimate the energy. Well, energy has to do with height because it's like the potential energy, and height has to do with squared, right? Because half gt squared and so on. It's the same dimension, but time is one over the frequency. It's reciprocal over the time. So it shows that the dimension at least frequency to the power -2. Okay? On the other hand, what is causing the dissipation? Now, this causing the dissipation is an interesting problem, and it's not the air, as I demonstrated. So what is it? I'm going to show. As the point of contact goes around in a circle, that's also the point of pressure. And that periodic motion of point of pressure makes the support vibrate and sends out, if you like, earthquakes, or if you like, phonons, which goes off the infinity carrying energy, does not come back. And that is what's the dissipating energy. So I'm going to demonstrate that for you. Let's do the experiment. And you should look at me directly, not with the camera. I'm going to put the camera too. But let's put the experiment on a good absorber of elastic energy, such as the human body. You know that the human body has been designed by God to absorb all sorts of shocks. So when how long the motion lasts, okay? Ready? And that's it. I have earthed the system, and all the energy escapes through my body to the ground. So this vibration or dissipation is what's causing the dissipation. So going back to that model of ours, I pressed something wrong. Okay, that's all right. Thank you. So the rate of the dissipation is, let's measure the time not in t, but the remaining time to the final time, which I'm going to denote because it's a singularity time at the end. Also, it's a time at which disk sings, you see, so it's d sing. So the remaining time, so d by d of sing minus t of e is, of course, minus d. To say it's an ansatz, so this is a theoretical model that I just invented, and you have to check against the experiment to see if it's reasonable, that dissipation rate of the energy is proportional to the flapping frequency. So the more it flaps, the more it generates. Because more it flaps, more earthquake it sends out. Okay? So let's accept. But then our analogy kicks in, because that frequency upstairs, bounce frequency, and downstairs flap frequency, I'm going to identify. Okay, so I can close the system because you see the time derivative of E has to do with the energy, with some power play. And it's easy to solve that differential equation. It's separated, so high school student will do. And it turns out that the E2 behaves like the remaining time to the singularity. Okay. And because the E has to do with the frequency itself, and we can now say that the frequency rises to the tune of the remaining time to singularity to the power minus 1/3. This minus 1/3 power is universal. It's really amazing thing. It's universal in the following sense. Whenever you have dissipation mechanism, which has to do with increasing collision, and the dissipation rate is proportional to the frequency, this comes up. After all, it's the only thing that I assume. So here's a very, very strong magnet that I brought. Made of neodymium or something, and one of the most magnetizable elements in the universe, and they are very, very strong magnets. And when I toss them in the air, you hear this. So you see they're colliding, and then eventually they stick. But that divergence, if you record it, is negative 1/3 as well. So I'm going to show experimental data. This was recorded by Ariel Amir, who is my collaborator in this project, who used to be a junior fellow at Harvard, but one of the really most brightest condensed matter physicists of his generation from Israel. And now he's a professor at Harvard. And the time is running from right to left because in Israel, they, I suppose, write Hebrew from right to left. So the squiggle lines in blue, the data. This is how the frequency is rising. It's log. And the red line is the theoretical prediction of the frequency, which behaves like remaining time to minus 1/3 power. And look, it goes smack through all the data. I mean, you get data like this for money nowadays. It's amazingly sort of good prediction. Yeah. So it is absolutely minus 1/3. With those magnets, it's a little noisier, but it's still very, very clearly minus 1/3. This is universal data. It's now time to conclude this talk, and we have seen that many of the toys that I showed you open up a rich variety of phenomena and ideas. So we start from chiming teacup and swirl versus circulation, rolling, not rolling, and jars of grains of slope and paper balloons, singing rim, and so on, so on, so on. And they led us to many, many sort of themes in applied mathematics, that is inverse problem, phase transition, singular perturbation, and, viscous inviscid coalescence, and what happens in between, and so on, inverse cascade and finite singularity, and so on, so on. And so, it's very legitimate to raise a much higher meta-level question. We all have, as scientists and the general public alike, the impression that the science is happening, including mathematical sciences, in some very fixed set environments. For example, labs, institutes, internet, and you can find information in the libraries, which is the storage of information, classrooms, and big research grants that you apply for. And of course, whenever you do so, cutting edge proposals and so on, kind of violent picture of, breakthrough and cutting edge. And I want science to be gentler and really much more humane. But anyway, all these things, these are all supremely important. And, these these are where we expect science to come from. Although I really don't like this imagery of, yeah, let's do it that way. So you might ask, well, in the meantime, Tadashi, why are you playing with toys? In guise of a reply, I'd like to share with you a little red passage of Aristotle's from 200 years ago, 200 years, excuse me. And it's in a book called De Partibus Animalium. And it tells the story of Heraclitus, who was one of the pre-Socratic philosophers, and who was from Ionia. And he's the one who said, Pantare, everything flows, and so on. So. And Heraclitus was some kind of scientific star of the time. Everyone looked up to him, a great natural philosopher. He was the equivalent of the professor of applied mathematics at the University of Washington nowadays. And so two young people came to meet this great sort of celebrity of the natural philosophy of the time, Heraclitus. And of course they were expecting, some white bearded person who was really sort of very, very famous and lecturing to 10,000 people, and then, sitting in front of a console of a supercomputer, and then maybe getting grants left and right and center, and so on, and worshipped by lots and lots of acolytes in the lab and so forth. But when they arrived to pay a visit to Heraclitus, they found him, but what they found was very, very different from that image. Here's what Aristotle says. Translation is mine. In all natural phenomena, he says, there is something of the marvelous. They once wished to meet Heraclitus, and when they entered and saw him in the kitchen, warming himself at the stove and playing with children, they hesitated. But Heraclitus said, "Come in, don't be afraid. There are gods even here. Enagar kai entausa theus." It's been a great pleasure and privilege to speak in Seattle. And to my esteemed audience, thank you very much for your patience, despite all the glitches and so on, and especially for your friendly company. And really, to Professor Deconinck, so for his kind hospitality and generous invitation, I would like to say thank you and have a great life. Yes, see some of these.
But there will be a reception in Lewis Hall after this. And then I should also remind you all that there will be a second colloquium tomorrow by Professor Tokieda in the Math Across Time series organized by the Math Department. That's going to be at...
I have my note here, so somewhere. Where is it? Yeah, so it's somewhere here. I can't find it. I don't know what happened to mine. Yeah, I can't find it. Okay. Oh, here it is. So it is at not to advertise 3:30. Yes.
So, any questions about any of the grades that you saw?
Right. So can you pick up? Yeah. Thank you. Oh, sorry. I'm so sorry to inflict this on you. So this was about, nothing is wrong in principle with something going as fast than speed of light if that something is not carrying material information, matter information. Okay, so there's a story that, Physical Review, this vast sort of conglomerate of various journals in physics, that's where, many of the physics papers go. They keep growing and growing in volume from year to year. It's amazing. So, in the 1950s and 60s, you had one volume of Physical Review every time that came out. Now it's kind of feels half a library or something like that. It's just the research is going far too fast and so on. So the calculation is that by 2050, if the physical reviews keep growing at the current rate, they'll start filling the shelves of libraries at the speed faster than speed of light. But there's nothing wrong with this because by that time they'll be carrying no information. Yes. Yeah. Oh, we're still trying to find it, but so the question was, excuse me, I would like to take that graph, and make, based on the immobility, narrower and narrower, and then make it disappear so that right-hand side of that, which is kind of behaving like viscous fluid mechanics, and left-hand side, which is behaving like inviscid fluids, meet, so that really something shocking must happen. And so the way we are doing this is to change, first of all, the shape of the grains, and see if that helps, and also do various parametric differences, and also put the grains inside the fluid and so on. So some variations of this, but we made the range quite narrow, but we haven't managed to make it zero. So we need some new ideas about this. And we also, of course, trying other things. For example, not only do we let these things roll down the slope, but we make the slope vibrate at the same time, or things like this. So all sorts of perturbations that will make that basin smaller and smaller. We haven't gotten to that end.
More questions? A little bit of personal question for you. So you, like in a mentioned that you were in different countries, and when you were giving the talk, you said that you were 1 year as a postdoc struggling in France, and then right now you're a professor
in Canada.
In Ontario. And then right now you're a professor at Stanford. So you give an advice to the students of how do you find your way in order to secure a job? How do you follow your passion?
Oh my goodness.
Sorry. Maybe that's more a question for the
Yes, I think so. And also it will give me time to think. Or indeed time to escape. But may I say very, very briefly that my sympathy is to all the young and not so young people in the various stages of life, PhD students and postdocs. I do sympathize. I had 8 years of postdocing on 1 year contract for all 8 years. So each time I arrived in a new place in fall, I didn't know where I would be next year. And I had to start applying. And how do you do this? I mean, you haven't done any extra work since last time. So it's really a terrible situation. And it's detrimental to all sorts of things in my human condition and in anybody's human. So my sympathies. I don't know why we kind of visited this upon ourselves in the name of research. But that's how it is. Sympathies.
Yeah. For the, sir, thank you for your talk. For some of the examples, like the ring that you were just a second ago, it makes sense how you would come up with that idea. The theory is friction with air underneath, so you get a ring. But for other ones, like the viscid-inviscid problem, did the toy example come from the concept, or did the concept and the problem come from the toy example that you perhaps noticed one day?
Thank you. So the question is, in which direction did any of these projects and ideas go? If I may answer that in about, it will take me 2 minutes. It has to do with how I started doing it. I used to be, I told Bernard this morning, a card-carrying topologist. And until I finished my PhD, that's what I was doing, and I had no interest in physics. But then I had a certain program, as people do, and during my really dangerous and distressing postdoc years, I started teaching myself physics to become a physicist, essentially, and I worked through Lambda-Lifshitz and so on and so on. And during that time, I noticed that, you see, in previous life, when I was doing pure and very high-level algebraic topology, it was very difficult to share what I was doing with friends and family, because it was exciting and some surprises existed, but I couldn't share. But physics, especially the macroscopic end of physics, have to do with daily life, obviously. So I decided that every time I figure out something, or indeed I would design a toy demonstration, which even only partially illustrates some of the amusement and surprise and indeed excitement of what I had. And as you can imagine, this was very popular among my friends and family. So now it's the other way around. Led by phenomena, I look and hunt for surprises in daily life. And whenever I find one, usually staring me in the face, but which I had never noticed in 50 years, then I start from there. And so all of these are phenomenologically led. So nothing comes from theory. For example, this, I was very glib and eloquent about the coalescence of, inviscid and viscous regimes and so on. I didn't know that it was happening. But when I started experimenting with grains and so on, naturally, so they started showing the nature is really kind to people who are humble, and who sort of yield to her, and who don't want to break through her or, cut edge of her and so on and so on. You just play with nature, you just are cuddled by nature, and then you discover lots of things.
Thank you.
I think that's a great note to stop and move on to the speaker again.
Thank you.